Yeah, thanks, Annie, for the kind introduction and thanks for the invitation to speak today. So, yes, as Annie's already told you the title, I'll press on and I'm going to start off with a very brief introduction to knowledge graphs. Probably most people here don't really need that, so I won't take too long on it, but at least just make sure we're all on the same page. So, what is a knowledge graph? Well, it's a set of nodes or vertices that are linked by some labeled edges in order to make them into a graph. And if we're in the RDF world, then a given pair of vertices and a labeled edge is often called a triple, and the sort of source entity vertex is called the subject, the label of the edge is called the predicate, and the target vertex is called the object. But we don't necessarily need to be in the RDF world to make knowledge graphs be useful. So the first thing I'm going to say is actually that I'll mention in a minute some of the nice features of graphs, but we should also recognize that actually they're in quite close correspondence with relational databases, and I could capture the same information that I have here in this little fragment of a knowledge graph. I could capture that in a relational database using this set of tables, for example. And there are well-known and sort of pretty standard ways of taking a graph and storing it in relational tables, and vice versa, taking some tables and translating them into a knowledge graph. So why bother with knowledge graphs at all when relational databases are very well established and they've been around for a long time and have a bunch of proven systems? Well, for one thing, I would say that knowledge graphs are more intuitive. This is a bit subjective. I'll come to some more objective reasons in a minute, but to be a little bit more objective about this intuitiveness, there are no foreign keys in knowledge graphs, which are actually a bit of a problem, I would say, with relational databases, because just looking at the tables, it's actually quite difficult to understand how the data is really all linked together. And we need to look at this, what can be quite a complex structure of interlinking foreign keys in order to understand what's going on. Whereas on the graph side, it's pretty intuitive just to look at that, navigate around, and everything's kind of directly captured in the graph. So no need for foreign keys. Also, the other thing about the graph is that the data and the schema are sort of, or at least part of the schema, as we'll come to in a bit, but at least this kind of backbone structure of the schema corresponding to the tables in the relational database are first-class citizens there in the graph, and we can see them in the graph along with the data. And the other thing I would say about the relational database is that the entities in the graph, like for example shard or Paris, they occur only once in the graph. So shard is here, Paris is here, and they're arbitrarily connected as needed to capture the data. Whereas in a relational database, these things occur multiple times in multiple tables. The other thing about the knowledge graph is that typically we actually use URIs rather than strings to represent the entities, and this has a lot of advantages, as well as being a convenient way of forming unique identifiers. We can actually think of a sort of linked open data perspective, and we can use common URIs. For example, instead of architectural structure, I can use this Wikidata URI for architectural structure, which makes the knowledge that I have in the graph more shareable, more easily integrated with other knowledge, and I can even use this URI to go off to Wikidata and grab a bunch of additional information about architectural structures. Another well-known feature of graphs relative to relational databases is that they're more flexible and more easily extensible. So if I decide I want to add information about architects to my graph, it's really easy to do. I just add some edges and some new nodes to the graph. If I can have a single architect or multiple architects, there's no problem there. And of course, I can also delete data that is no longer applicable. For example, those of you who were paying attention may have noticed that I have this edge saying that the UK is a member of the EU, which unfortunately is no longer true. So we should delete that edge from our graph. And I'll come back to this issue of deletion later because it has some interesting features when we consider the interplay with rules. And of course, we're here primarily to talk about rules, so that'll be interesting. And finally, another nice thing about the graph paradigm is that it facilitates other kinds of queries, such as navigational queries, similarity and locality queries that may be related to things like the structure of the surrounding part of the graph, or things being close together in the graph, or whatever. One thing I'd like to mention, though, is on the downside, a very powerful and widely used feature of databases is views. And there isn't, at the moment, looking at this graph, an obvious corresponding feature to views. And as I say, these are widely used in databases for things like integrating and restructuring the data, for security, for query simplification, and so on. So again, I'll come back to that in a minute. Okay, so I know that was very fast, but I guess that was all stuff that most or all of you are familiar with. So I wanted to make sure I saved time for the interesting stuff, which are challenges and hopefully some solutions. So a very well-known problem with this kind of graphical representation of knowledge is the problem of vague semantics. So I mentioned that the graph is sort of intuitive, and this is very seductive, but it's actually also a bit illusory, as has been pointed out, since the early days of AI, when graphs were used to represent knowledge. And this is a little example from some work of Quillian going back to even to the 60s. And he was pointing out that, we have, for example, in this graph, we have this edge connecting cat to black, labeled has color. And, intuitively, this is saying something like cats have color black. But it's not completely obvious what this really means. Does it mean all cats are necessarily black? Does it mean there exist some cats that are black? Or perhaps it even means that the only things that can be black are cats. So everything that's black is a cat, which, obviously intuitively to us is silly. But from a system point of view, if we want to use this knowledge, it's not all that clear what the real meaning is. And we can see how this comes back to bite us if we think about a query over our knowledge graph that is for, say, give me all the architectural structures that are located in the EU. So it seems sort of intuitively obvious that the Eiffel Tower should be in the answer to this query. We can see the Eiffel Tower as a type of tower, which is a kind of architectural structure. And the graph also tells us the Eiffel Tower is located in Paris, which is the capital of France, which is a member of the EU. So as a sort of human being, I'm tempted to say Eiffel Tower is in the answer to this query. But it's not at all clear how our knowledge graph system would actually come up with this answer. It really depends on quite a lot of implied semantics, implicit semantics, to do with the relationship between the type and kind of edges, which intuitively leads us to believe that the Eiffel Tower is a type of architectural structure, and similarly the Shard. And it also depends on some intuition about the semantics of location, capital of, and member of edges and how they interact with each other. So how are we going to solve this problem? Well, my proposal for the solution anyway is that we deploy logic. And I mean, logic was actually developed exactly for this purpose, for explicating the semantics, investigating and explicating the semantics of knowledge. And it's very intuitive, actually, to establish a correspondence between our graph and logical statements. So the bottom half of my little graph fragment here consists of ground facts, which correspond very naturally, which I can map very naturally to ground atoms in logic. I actually have a sort of built-in semantics for type edges here, so I take type edges to mean that these triples here correspond to unary ground facts. So this triple here corresponds to the unary ground fact stating that the Eiffel Tower is indeed a tower. And all other edges in the facts here, like location and capital of, correspond to binary ground facts where the label on the edge is the predicate and the other two, the two entities, the two nodes in the graph are the two components in the ground fact. So this triple here corresponds to the ground fact, the binary ground fact saying that the Eiffel Tower is located in Paris. Okay, and the upper part of the graph, the kind of edges, again, very naturally correspond to these universally quantified rule axioms that just capture the subclass relationship. So, for example, this one here corresponds to this axiom saying that for all x, if x is a tower, then x is an architectural structure. And if I take all of this lot together as a sort of first order theory, then that's sometimes called a knowledge base, or in our case, we're calling it a knowledge graph. Another nice thing about the correspondence to logic is it also tells us immediately how to answer queries. So query answering, oh, sorry, I've jumped ahead of myself. So once we decide that we're going to use logic, an additional benefit we get is that we don't need to restrict ourselves to these axioms that we get by translating kind of edges into these sorts of rules. We can actually introduce in principle arbitrary first order axioms, and we can use these to axiomatize the intended semantics of other kinds of edges. So, for example, I could add these two axioms that axiomatize my intended semantics of the interaction between location of and capital of edges and location of and member of edges. This semantics isn't built in. I've added this axiomatization, and we can discuss whether or not this is correct or incorrect. But at least here I've formally explicated my intended semantics for those edges. Okay, and back to where I jumped ahead to. So once I've done all this, I can actually use the logic also for query answering by just using logical entailment to define the semantics of query answering. So for example, Eiffel Tower is in the answer to my query for architectural structures located in the EU, just exactly because these two ground atoms are entailed by my knowledge graph in its logical form. Equivalently, we could think of this as the fact that my axioms here entail some additional edges, they entail this type of edge, and they entail this location of edge in my graph. Okay, so actually you'll have noticed that many of the sorts of axioms that we typically use actually correspond to these universally quantified implications, aka rules, and we very often abbreviate these when we write them down by ignoring the universal quantifier at the beginning, which I'll do from now on. Another thing that's nice about being able to use these kind of rules is that actually I now have views again. So we can think of these rules as actually corresponding to, in some senses anyway, to views. And for example, I could add this this query that I just mentioned, architectural structure located in the EU. I could add that query as a rule and introduce a new predicate EU structure as the head of this rule. And as we know, this is exactly what views do. They basically just define a new predicate or a new table, if you like, which is instantiated by which is defined by a query. And that's exactly what this rule here is doing. So by adding rules into the mix, I've actually brought back views, and I can use these kinds of rules for all the same sorts of purpose that views are used for in relational databases. I can use it for integrating and restructuring knowledge, as in this case, where I introduce this new predicate EU structure. I can use it for security, so maybe I only allow some users access to EU structure, but not to the rest of the graph. I can use it for simplification, so I can reuse this EU structure in future queries to save me having to write out the whole body, all of this lot in the query, so make queries simpler. And I can use it for optimization, and I'll come back to this in a bit when we talk about how to implement knowledge graph systems. I can use it, for example, by materializing EU structure into the graph so that I don't need to compute that at query time. Actually, rules are more powerful in general than the sorts of queries that are supported by most relational databases, because I'm allowed to have recursive definitions. And for example, these location rules here, we can see that these are recursive. And this is actually critical in many applications where we need to deal with things like partonymies, connectivity, causation, and so on, which often involve chains of unknown length of edges in the graph. And to deal with that, we really need recursive rules. Okay. And finally, another nice thing about this correspondence with logic is that we already have a lot of experience of how to devise algorithms for reasoning in logic, which we can use to implement systems and do query answering and so on. If we want, we can check or prove that the algorithms that we're using are even correct, in the sense that they're sound and complete for the semantics of the language. So it's all looking good. We store our knowledge in a knowledge graph, which we've seen has a bunch of advantages. We establish a correspondence with logic, and we just use logical querying to do our query answering. So we've solved all problems. Sadly, not quite, because this rather annoying chap here showed us a long time ago that there are issues with problems, and in particular, we know that the first order logic entailment problem is actually undecidable. So, and even if we choose a slightly more restricted logic that we can show is decidable, often such logics still have rather high complexity, and so it may mean that reasoning takes an infeasibly long time, and in particular, query answering takes a very long time, and obviously, that's not going to be acceptable for applications. And this has been a sort of bugbear for AI for for many years, and logic actually had a pretty bad rep. At least back in 10 or 20 years ago, people were very shy about using logics because prototype systems had been shown to not work very well on larger scale problems. So how are we going to deal with that? Well, we have to bear in mind that these are only worst case results. So even if the logic's undecidable, we still might be able to decide some problems. And even if it's intractable, then some problems may still be tractable. And so what we can do is we can study knowledge representation languages to try to find a good balance of expressive power and computability. And we can design reasoning algorithms that work well in typical cases, and we can develop highly optimized implementations. And Annie mentioned I spent a long time working in the area of description logics, and basically this idea is the raison d'etre of description logic. So there are a family of KL languages that are usually subsets of first order logic that provide a range of different constructors that can be translated into first order logic. And the idea is to try to find combinations of these constructors that give a fairly expressive language that works for the sort of KR task we're trying to perform, but for which we can still build effective reasoners. And this description logic research had been pretty successful and had kind of mapped out a whole landscape of different language first order logic subsets, with a lot known about their formal complexity and also not a lot known about their implementability. And there were even several practical systems that had been developed for relatively expressive description logics. And for this reason, the W3C decided to use an expressive description logic, one called SROIC actually, as the basis for the W3C OWL language. So, okay, hopefully now we, as usual in research, we had some good ideas at the beginning. We'll use a knowledge graph. We'll use correspondence with logic. We'll use logical reasoning. There were some kind of potholes along the way because it turned out that that can be quite hard in practice. But then we found these description logics. We had highly optimized systems, and we developed our nice web knowledge graph language that exploits our knowledge about description logics. And actually this was pretty successful, at least for what I would call ontology-centric applications. So this resulted in the development of a very large number of ontologies, and reasoners such as Hermit and Elk have been very successfully used to identify errors and inconsistencies, to compute the class hierarchy and so on. And this is widely used in domains such as medicine and life sciences in particular, where ontologies like the SNOMED ontology are deployed in practical healthcare systems now in more than 70 different countries. So we'd have to say that that actually is a huge success. But even so, this turns out to be a slightly sort of niche application, I would say, because the size of these ontologies is typically limited. Even the SNOMED ontology, which is one of the very largest ontologies that we can find out there, is a few 100,000 classes. And when we look at data-centric applications, of which I would postulate there are many more than ontology-centric applications, here what we tend to see is a slightly different picture, where we have very large sets of facts, and knowledge graphs of this kind can be greater in size than 10 to the 9 different edges. And the main reasoning task here is not so much classification of the ontology or reasoning about the kind of relationships between different classes or concepts, but rather query answering. And in the RDF setting, that would be Sparkle query answering. And these sorts of reasoners I mentioned in the previous slide that deal with expressive ontology languages, such as the full OWL languages, don't scale very well to this task. Query answering typically reduces to multiple entailment checks. Each one of these checks can be extremely costly, and this makes it rather difficult to perform efficient query answering at scale. So, as I mentioned before, as typically is the case in research, it's a bit of a roller coaster ride. We were doing so well, but suddenly we went down the roller coaster or hit another pothole in the road, to use my other metaphor. So what do we do about that? Well, this was where the development of profiles came in OWL 2. So the idea here was to identify some smaller subsets of the OWL language that had better computational complexity, and also for which we knew some algorithmic techniques that were better suited to query answering. And in particular, we identified three subsets, which we called QL, EL, and RL. And one that proved to be particularly interesting for this group anyway is this RL language, which is based on the fragment of OWL that corresponds to, that intersects with data log. So it's basically the intersection of data log and description logic, which is also sometimes called DLP, description logic programs. So, well, actually, just to go back one slide, I should also mention this QL subset, which is based on the DL light description logic. And actually, in a way, we could think of that as being the intersection between description logic and relational databases, because the whole point of this QL fragment is that we can use a query rewriting technique for query answering. In contrast, in the RL technique, in the RL fragment, the most common technique is materialization. Although we don't have to use materialization, we could also use some sort of backward chaining technique. So I'm just going to say a little bit about these query answering techniques. So as I mentioned, for this OWL QL fragment, we can use query rewriting. And the way that goes, as a little example, is that we take this structure, this query, for example, for architectural structures, and we simply expand it by treating the axioms we have in our ontology as sort of backward chaining rules. And we expand the query by saying, well, if we need architectural structures, then we also need towers. We do a bit of backward chaining there. And similarly, we also need buildings. So we expand the original query into this union query that returns all of the architectural structures, all of the towers, and all of the buildings. And this works quite nicely, and it has quite a lot of advantages because we can leave the data in the original relational databases, if that's where the data is sitting in legacy databases, and we can actually translate this query into a union query over the database, which looks like that if we had the data in the same structure, in the relational database structure that I showed in my initial example of the knowledge graph. The big disadvantage, though, is that in order to be able to do that, the language has to be really weak. I mean, obviously, the language actually has to have the same complexity as query answering in relational databases, which is inside log space, and this imposes some severe restrictions on our representation language. For example, we can't have recursion anymore, so we can't answer this example query I had We can't use this rule that we were using to capture the interplay between location of and capital of. And as I already mentioned, these kinds of recursive rules are really important in many applications. So the other way we could go is that we can use this OWL language. And in this language, the most common method of query answering is to use materialization. So we simply run the rules in a sort of forward chaining way, as I'm sure you all know. So we just treat these axioms as forward chaining rules. I already actually represented them as rules in the previous slides. And we just exhaustively apply those rules until there's nothing else to be added to the till no new information is derived. And in this case, we end up with this knowledge graph here with the addition of these 6 entailed edges. And then we can just answer our query directly over the materialized knowledge graph, which has the advantage of being very efficient. The downside of this technique, or one downside of this technique anyway, is that we're going to use more memory. So we add all of these new edges to the graph, so the graph can get bigger. In the worst case, polynomially bigger. And another perhaps more important in practice, I would say, problem is if the information changes, and in particular, if we delete information. So if you recall, I had this example where sadly we have to delete this edge here because the UK is no longer in the EU. And when we do that, we really should delete this edge as well, because this entailed edge depends on the existence of this edge here. But this requires some sort of truth maintenance, and that's not so easy. I don't really have time to talk to this, but actually we can also use this forward chaining materialization technique. We can basically use RL to also do query answering with EL if we add some sort of filtering technique at the end. But I'll leave the slide in the slide deck, and any of those of you who are interested can look at that. But I won't speak any more to that in this talk. So RL seems to offer some nice advantages. It's quite an expressive. It's quite expressive, but we can also do fast querying on large graphs. The problems with that are that materialization, the process of materializing all these edges, can be costly in additional memory, I already mentioned, but also this can take potentially a long time. We can do that as an offline process, but even so, if it's going to take, days or even weeks, that could be pretty inconvenient. And if we change the data, in particular if we delete edges, we may need to repeat the whole materialization process. So these ideas, the fact that RL seemed to be quite a promising language for these data-centric applications, but also that there were some challenges there, motivated us to do some research into materialization-based query answering systems for OWL, and in particular to develop our RDF-OX system. And the idea behind RDF-OX is that we wanted to optimize materialization by exploiting modern computer architectures that have typically very large main memories and also multi-core architectures. And we also wanted from the very beginning to support incremental maintenance. So if we delete edges, we don't want to have to repeat the whole materialization process, but we want to be able to do this kind of truth maintenance. Another thing that was really critical to our research, why we wanted to develop RDF-OX in a research group, is that we wanted to use algorithms that were provably correct. And this might be sort of obvious. You might think that, well, surely everybody uses algorithms that are correct. But actually, that turns out not to be the case. And when we first developed RDFOX, we were doing a lot of tests comparing RDFOX with other systems, for performance testing primarily. But then it turned out that often we were getting different answers. And when we pushed into this, we were able to see that many of the other systems that we tested against were just broken. In fact, almost all of the other systems that we tested against turned out to return either wrong answers or just crashed, or for some queries, they'd go away and just, churn indefinitely. So I think basing such a system on algorithms that are developed and proved to be correct is a really important feature and something that we as researchers should be able to contribute to. So how does it all work? Well, first of all, one of the core parts of RDFOX is an optimized in-memory data structure. So we store all of the triples in memory, mainly in this kind of large triple table. And this triple table is multiply indexed, which is a sort of relatively common feature for RDFOX. But we try to make sure that this triple table, that this data structure is also reasonably economical in terms of memory. And we can store on typical entry-level servers, we can store more than 10 to the 9 triples, and we've stored more than 10 to the 10 triples on large servers that have, that have more memory. And this isn't enough for every application, but it turns out that it's really more than enough capacity for most of the sort of industry applications that we've seen. So one of the ideas of using this in-memory data structure is that it facilitates parallelized materialization and very efficient parallelized materialization. And the way we do that is that we try to avoid locking wherever possible, and we do that by using these compare and store instructions that are supported by most modern processors. And this allows us to dynamically distribute the workload so that we can keep all of the processors really working to maximum capacity. And I have a little example here of the kind of thing that you can do. If you look at this data structure here, you can see that the NSP list has this 132 triple, and then the next triple is 134. But say two of the threads want to insert new triples after this 132 triple. So they both add the next pointer to their own entry in the table, and then they both at the same time try to change this pointer in the first entry in the triple table to point to the new entry. But only one of those succeeds, and the second thread recognizes that it failed in its attempt to update this pointer because the CAS instruction was used for that. So it tries again. It sets its next pointer to there this time. It tries again to set this pointer, and it succeeds the second time. And now we have a complete new linked list in which the two entries have been added without any conflict and in a sort of lock-free way. Or we can think of this CAS instruction as being a sort of single memory location lock in a certain way. For more complex instructions, for more complex updates to the table, we also use the CAS, but we have to do that in a cleverer way by sort of locking entries in the table by putting a special lock triple in there using the CAS instruction. So by doing it this way, we can actually get really high usage of the cores. And this is a little graph that shows actually 32 threads running hyper-threaded on a 16-core machine. And we were, in the best case, we were able to get 20 times speed up on only a 16-core machine, which it might seem counterintuitive, but this hyperthreading helps to avoid memory stalls. And finally, another aspect of our research, which, as I was mentioning, was really important, was research into these kind of truth maintenance algorithms. The basis for that is the DRED algorithm, which has been around for a long time in the database area, which is an algorithm that's used for view maintenance in databases. And the way this works is that it basically, when you retract something, it has a deletion phase, which uses some sort of backward chaining through the rules, but it does over deletion. And then it rederives any facts that have for which it can find alternative derivations that don't use the deleted fact. The problem with that algorithm is that this deletion phase can sometimes be overeager, it deletes too much, and so we developed the BF algorithm, which sort of interleaves the backwards and forwards phases in order to avoid over deletion, and that works pretty effectively in practice. Okay, so time's getting a bit short, so I'm just going to sort of whiz through this last part reasonably quickly and then leave some time for questions. So one of the things we wanted to do when we developed RDFOX was we really wanted to show that this kind of system can actually solve real problems out there, in industry. But unfortunately, as you all know, it's very difficult to persuade industry to really use systems that were only developed in research. Partly the problem is lack of support, and partly the problem is lack of infrastructure. And so we decided to found this spin-out company, Oxford Semantic Technologies, to develop a sort of commercial version of RDFOX and see if we could really deploy that in industry. So one of the first things that we discovered was that actually this OWL-RL language leaves quite a few features to be desired in realistic applications. And one of the main things that we really needed to support was much more powerful features to do with data types and values. So we had to do things like more built-in functions, aggregation functions, and so on. And also constraints and negation as failure is an important feature that a lot of applications use. So we had to add support for that. The other thing I mentioned was infrastructure. So when the system came out of the research lab, as is, normal, it was quite minimalist, and it really just looked like this with the core engine, a Sparkle interface, and a command line interface. And within the company, we had to spend a couple of years just adding all of the usual stuff that you really need in order to support applications out there in the real world. Okay, so I'm just going to finish off in the last few minutes just by mentioning a few of the applications where we have successfully managed to deploy RDFOX in industry. I think one of the most interesting and successful ones has been configuration management. And one of the applications there is at Festo, which many of you probably know already. It's a large company, a world leader in the manufacture of production line equipment. So they produce, everything from conveyor belts to robots and who knows what that modern production lines require. But these are extremely complex and expensive systems that have numerous thousands or even tens of thousands of components. And Festo are now using RDFOX to store knowledge about all of these different components, including the attributes and constraints, compatibility, and so on, what constitutes a valid configuration. And all of these are stored in data and rules. For example, there might be a rule that says a DC motor is compatible with or a motor is compatible with a power supply, just in case the power supply provides the same kind of voltage, DC in this case. It provides the same level of voltage, 12 volts, and it provides at least as much current. So this would correspond to a little rule, which is just represented here in RDFOX syntax. And this allows the system basically to check whether configurations are actually valid. And Festo are now using this live on the configuration management tool. So if you're developing or buying a production line system from Festo, they'll use a rule system to check that it's actually all going to work when it's installed. Another interesting application, another, I would say, long-standing application of rule systems is data integration, and we have a system running at Dow Jones where they integrate data from multiple sources, information about companies, stock markets, articles, and so on. And they store all this in the knowledge graph, and they basically use this to provide a sort of integrated query answering service, which allows them to answer queries about competitor companies, retrieve articles with different kinds of constraints that cut across all of these different data sources. And finally, I should mention semantic search and browse is another interesting application. We have several collaborations in this space. So one collaboration we have with eBay, where we're looking at the use of a knowledge graph. And actually, you can see in all of the e-commerce companies have some kind of a knowledge graph that stores knowledge about products and their their features and the relationship in a sort of hierarchy, and that can use rules to help a more intelligent browsing of the products and check that the customers are really getting what they want. Okay, and I'm going to even skip over this one because I'm running out of time, and I want to make sure we've got time for questions. So just to wrap up, I'd say, so knowledge graphs are a powerful tool for representing and reasoning about knowledge. We've seen a bunch of interesting applications. We've also looked at technical challenges, which include complexity, scalability, extension requirements, system infrastructure, and I've suggested some solutions that are based on a combination of foundational research and systems engineering. Okay, and I'll just mention that this isn't just my work or even just the work of my group, but obviously is the work of a great many colleagues and collaborators and funders that I've had the luck to work with over the years. So thanks to all of you guys, even if your photo didn't make it into the rogues gallery here. And that's it. I'll finish there. I'll leave up a couple of references for background reading, and I'll be happy to take questions in the remaining 10 minutes, I think.
Yes.